Is my screen visible?
Yes, sir, visible. Audible.
It is visible, right?
Yes, yes, visible.
Okay, so let us start today's session. Today's session will be mostly on this how this residual stress generated during welding because of some thermal interdiffusion during welding. What is the origin of those thermal stresses? What are some typical residual stresses are there in welding zone? What will be the effect of them? And then maybe for some questions we will discuss the measurement techniques of residual stresses in weldments, and then then we can also discuss this the control of removal or at least reduction of residual stress during welding, right? So these things we will try to cover during this session. So let us start. So in question one, it says which of the following is not among the preheating method used in welding. So as we know, and we have already discussed in the earlier lecture, that you in general do some kind of pre and post heating to reduction some kind of uh, deterioration or residual stress or some kind of distortion whatever is happening during welding. So physics point of view, what happens during welding because of temperature. So so like if you see, heat is basically it's kind of thermal energy, right? So heat is stored or can be generated or transported, or it can be transformed by metals, correct? So while it is of little concern to the heating of welds, thermal energy can be transferred to either mechanical or electrical energy by metals, right? So and also in addition, under certain circumstances, metals may generate thermal energy. So what is the principal concern? Like the principal concern is the storage and transport of thermal energy, right? Storage and transport. So how does it happen basically, right? What is thermal energy? So if you see, thermal energy is at the temperature of interest, or you can say it's some atomic vibration, right? The result of this vibration phenomena is that adjacent atoms in a crystal lattice structure will be affected by that vibration of these neighboring atoms through some forces transmitted via metallic bonding, right? Now now let us assume for some completely ideal isotropic material. So I am assuming some ideal case. So for ideal isotropic material, for huh, am I audible? Hello?
Yes, you are audible.
Yeah, okay, great. So, for a completely ideal isotropic material, what can be the equation for this heat conduction? So, it's basically Fourier series of conduction, right? Or else you can write down it in this manner: delta 2 delta x2 plus delta y2. What is d here? D is basically thermal diffusivity, right? What is diffusivity? Correct? K by rho c. And what does it consist of? This thermal diffusivity, it consists of a combination of physical properties of metal, including this, as I was telling. You have density, then you have heat capacity, then you have some ability to transport the heat, which is conductivity. So at temperatures much higher than those of weld fusion zone, a second mechanism for heat transport occurs. So it's kind of valence electrons, which are quite mobile in a metal, can provide a mechanism for heat transport, right? So these are some basic raw concepts of what happens during temperature distribution during welding. Now now if we try to understand what is a mechanical effects of heating. So mechanically, what will happen in your weldments when you are heating something? So so basically, you are increasing a temperature for a given mass of metal, right? So as the temperature of a given mass of metal is increased, several important changes can occur. So what are those changes? What will happen to a metal if you are heating that up or rising the temperature to some extent? So basically, first the metal increases in volume, right? So metal will increase in volume, right? And then, so basically, although the volume changes is manifested as a different linear dilation in different crystallographic direction, uh, like the multiplicity of this lattice orientation in most metals of engineering interest allows for essentially uniform and some expansion in all directions, right? So this thermal expansion is matched by an equal amount of thermal construction upon cooling. So basically, you will have some thermal expansion of the metal, and then you can have some thermal contraction when cooling starts. Correct. However, if the material is not heated uniformly throughout, as is always the case with weldments, so it never happen that you are heating it up uniformly. So what will happen? There will be inelastic deformation. Correct. So because of some inelastic deformation, you will end up with some kind of distortion in your weldments. है ना? So the thermal expansion and contraction, what it generates a kind of strain or stress in a weld component, which serves to cause this added distortion, or it can create this inelastic deformation, as I was saying. So and also this serves for this distortion in the part, right? So whenever you are analyzing this, what will be my residual stress in the weldments during that time, the coefficient of thermal expansion contraction is the most important parameter. Correct. Now let's see if the surrounding base metal is preheated. So it will of course expand, it will try to expand. Now as the weld is solidifying, there will be some difference in temperature between the weld and the base metal. and that temperature difference will be less in preheated weldment. Correct. So one thing, you are heating it up from 25 degrees to, let's say for aluminium you are heating it up to 660. So the delta T will be somewhere in between some 580, I don't know, 660 minus 25. And then if you're preheating to some, let's say 200, and from 200 you are reaching the melting temperature, you're reducing the temperature difference, right? So because of reduction in temperature difference, what will be the result? The result will be less thermal contraction, correct? And that also reduces the amount of this inelastic deformation and so-called residual stress that develops during this thermal diffusion into the metal surface. है ना? Now, what can be a metallurgical effect of heating? Hmm? So, metallurgically, what will happen during if you are doing some heating of the metal? So, your metal will act as a large heat sink, right? Due to this large available heat sink represented by this base metal of a weld, the cooling rate of the welds are much faster than the cooling rate that could be achieved in ordinary heat treating quench practice. So the base metal has a like it can have some composition designed and optimized for heating, cooling, and mechanical forming conditions of a metal good production facility. And yeah, there can be some effect of heating can be on this corrosion resistant cracking, corrosion cracking also can be reduced by preheating. What is corrosion cracking? We discussed it in the earlier lecture also. So, kind of hydrogen is a significant contaminant in welds on a variety of metals, right? So, it can deteriorate your weld metal property if you're because of some solubility of this hydrogen into your uh, fusion material. Now, in terms of preheating, what are the different processes? What are the different processes you can use for preheating the metal? So you can have something called, there is induction heating, then there is flame heating, then there is oven heating also. What else? I don't know. Okay, let us stick to this three only. Now, how induction heating will work? How does it work? The induction thing. Any guess? So if you see induction heating, it's basically creates a magnetic field, right? It creates a magnetic field that generates this eddy current within this base metal, and you are heating it internally from within this through these induction accessories. such as there can be some cables, or there can be some blankets, or some coil of wire like this, and you are basically applying some kind of magnetic field to generate this eddy current. So what are the pros and cons of induction heating? So in terms of advantages, induction heating offers a kind of quick setup, often in less than 5 minutes maybe, and a fast rise of temperature can happen in induction heating. So, and also in induction it produces a uniform heating area, so making it easy to achieve and stay within a strict temperature window, right? And this process can be extremely efficient, and it doesn't require any kind of any person to observe what is happening really. Huh. So there is nothing to observe as such, right? The process is very much efficient, and induction provides safety benefits also, since output coils don't get hot or create an uncomfortably hot environment for welders. And in terms of disadvantage, what can be the disadvantage for induction heating? So basically, the disadvantage is your cost, really. So induction can have some higher initial cost, and require some operator training to ensure proper how it should be wrapped, how what should be the rate of heating. Uh, so those things can be some disadvantage. So for the sake of saying something, it can be some disadvantage. Anyhow, this is the initial investment is higher. Now, in terms of open flame, how does it work? So as I was discussing in the earlier day, also it is like a gas welding, right? So here you are producing some flame through some mixture of gases. You are burning some gases through oxygen, and basically the operator use a fuel gas and some compressed air torch, and then apply the flame directly to the metal part. So that's how it works really. And what is the advantage? It, as you are having already a torch, and additional equipment does not need to be purchased for preheating. So it's basically it requires very much or no operator training is really required. And in terms of drawbacks of flame preheating, mm, what should I mention in terms of drawbacks? Uh, like it can include some inconsistent temperature uniformity, like it happen in induction heating. The heating area will be uniform really. What will not happen in open flame, there must be some kind of distribution of heat source. It is not uniform over all the surface. Got it right? So there can be some Gaussian distribution. I'm not sure what distribution is there. I'm just talking about that. Somewhere the heat flux can be less, somewhere heat flux can be more. It will not be uniform for sure. And then a slower time to temperature. Basically, it requires more time to the rate of heating is very slow here, and the process is, you can tell it some inefficient process. And also there can be some smoke, some gases also produced while using this open flame now. And in terms of cost, it's of course really cheaper compared to this induction heating. One more heating process I forgot. There is resistance heating also. So you are well aware of this resistance spot welding, how it happens. Resistance spot welding. So it takes the advantage of the electrical resistance of the metal, right? If your metal is having if your metal is having higher electrical resistance, can it produce heat? Let's say if you are trying to weld copper with resistance spot. Can it weld copper with resistance spot? What is much easier, welding steel with resistance spot welding, or welding copper with resistance spot welding? Of course, steel will be much easier for resistance for welding because the electrical resistance is much lower for steel. Cannot dissipate heat quickly compared to copper. And so resistance based heating, how does it work? So it uses electrically heated ceramic pad placed on the base metal, and those heated tiles transfer the heat to part through some radiant heat or some conductive heat where the pads are in contact with the part. Correct. And in terms of advantage, resistance setting can deliver some temperature consistency if the system is working accurately. And huh, that's it, I think. And in terms of disadvantage, the cost, of course, the cost of using resistance can be higher, especially like since the method is often contracted out of third party who controls the schedule and timeline. But these are some secondary things. And then there are something called overheating, as I mentioned here, that also can be used for preheating purpose. And here uniform heating is possible since the entire part is inside the oven. You know? So it's also a good option when an entire large part must be heated and when the operation needs to do in batches. And in terms of disadvantage, ovens can be quite large and require some connection to an electrical outlet. So they are often permanently installed in one location and don't offer mobility. So those are some of the advantages and disadvantages of the procedures of this preheating thing. So coming to the question, coming to the question. It says which of the following is not among the preheating methods discussed? Flame preheating, there is induction preheating, both, right? Any question, whatever I discussed till now?
No questions.
Right. So here preheating a low alloy steel prior to welding is used to minimize what? To minimize excessive distortion, to minimize porosity, to minimize weld cracking, a lack of fusion. As I was saying that preheating is basically what is thermal strain? What is thermal strain? First, what is thermal strain? Let's say you have a metal plate like this, and let's say this side is fixed, and you are applying uniform heating over the surface. It will try to expand, right? So whenever it is trying to expand, at the end, what kind of stress you are getting? Mhm. So at the end, you will get some tensile stress, right? It will try to expand, but within the material itself, as you are as you are as the metal is experiencing this tensile strength within the material, it will feel some. So if you are taking this section, it will feel some compressive strength to compensate that one. So this kind of stress is called compressive residual. So here I am discussing in crude manner, of course, but this idea is as simple as that. So here, what will be the thermal strength here? Alpha delta, right? So alpha is your coefficient of thermal expansion, correct? So whenever you are having this temperature difference high, you will end up with some higher thermal strain. If your thermal strain is high, what will be the thermal stress then? Let's say we are in elastic range. I'm not talking about some deformation or inelastic deformation or plastic strain. We are in elastic range. So whatever strains you are getting, it can be recovered. What will be the thermal stress here? If the thermal strain is alpha delta, in elastic range, what will which property will relate your stress to strain? Are you aware of this Young's modulus? So your thermal stress will be E alpha delta sigma thermal. है ना? So basically preheating of low alloy steel, as I discussed earlier also, it can minimize the risk of excessive distortion and weld cracking. So cracking, of course, there can be some shrinkage. So in your casting also, you have come across this shrinkage term, shrinkage porosity. So during the heating, the material is trying to expand, while cooling, it is trying to contract, right? And because of that, because of the shrinkage in the material itself, there will be this cracking tendency in your fusion material. So whenever your temperature gradient will be higher, your cracking tendency will be higher. That's why you are doing some preheating and trying to what should I say, trying to maintain this temperature gradient or increase this temperature gradient gradually. It should not happen suddenly. And be, if you are doing anything suddenly, there will be impact. Basically, something will happen for sure. So you need to do as well for the cooling also. You cannot have some very fast cooling rate, right? So there should have some optimization in between what should be your heating and cooling rate. Any question?
No questions.
So this is something from induction heating. So I talked about this advantages and disadvantages of induction heating. So here there are three statements, like a high heating rate is possible, temperature can be controlled within a narrow zone, and it says low initial. Of course, this is not true. Flame preheating is much cheaper. Uh-huh. So these two are correct, right? So in induction heating, because of those induction coil and those magnetic field and eddy current generation, the rise in heating is very quick here. And also you can have some control over your heating and your temperature generation over a uniform area, which can be very much narrow. Coming to this residual stress, what can be the causes of residual stress involvements? So as I was saying, these residual stresses are those stresses that would exist in a material or structure after all external loads are removed. Correct? It is some internally generated during the process. So what can be the other name of residual stress? It can also be called in some internal stress or some inherent stress, since they are present in a material or structure before external loads are applied, correct? Or else you can say as some reaction stress, because some kind of reaction is happening to a localized or differential strength. Now now what can be the causes for this residual stresses? Residual stresses can arising from any of the several sources, but always as the result of an like unbalanced situation of strain. So anytime you are having this unbalanced situation of strain, this residual stress must arise. And also this can arise from some non-uniform plastic deformation, especially when you are performing some cold rolling or forging action or any kind of forming action, or let's say you are doing some machining due to this unbalanced local deformation caused by this material removal process, right? All of these are mechanical processing I'm talking about. And this thermally induced residual stress can arise from any process that involves heat, right? So there are two mechanisms. One is deformation based, and one is simply thermal diffusion based, right? So, huh, what I was talking, this thermal induced residual stresses, right? So, thermal induced residual stress can arise from any process that involves heat, right? Whether that process is primarily a thermal process, such as there can be some heat treatment or can be welding. So, in those processes, only heat is basically uh, taking part for your residual stress. In machining, for example, one source of residual stress is localized heating from the friction of this uh, from from the friction of this work done by the cutting tool and workpiece, right? So when expansion and contraction associated with this heating, and after this heating there can be subsequent cooling, that is not free to take place because of this constraint imposed by surrounding material that has not been heated. So let's say you are machining something. How was it? This is my cutting tool. This is my chip, maybe, right? So there must have some friction of this cutting tool and workpiece, and because of that your heat is generating, and when expansion and contraction associated with this heating, and then the subsequent cooling, that is not free basically, right? Because of this you are having some constraint surrounding this material that has not been heated. So at certain zone you are heating, you have some surrounded with zone where you have not heated up, and that is also you have seen in your fusion zone. So here you are melting, there are subsequent microstructure form around this fusion zone, you know. So yeah, So the most common source of thermal induced residual stress or thermal process. So as I was saying, heat treatment at various stages in manufacturing can lead to residual stress, and from quenching, the outside part cools, and there is basically in the cooling rate, there can be difference basically when you are quenching. So for that also residual stress can generate. What can be the other reason? So in terms of, let's say, for in terms of non-uniform plastic deformation, what will happen for non-uniform plastic deformation or non-elastic strain? So when a metal is heated uniformly, it expands uniformly, and no thermally induced stress arise that can lead to either this locked in stress or distortion. I'm talking about this locked in stress. This is another name of this residual thing. Hello. So on the other hand, if you are doing heating non-uniformly, there always be thermal strains and stress develop. Correct. Now, these thermally induced stresses, which can become locked as a result of the structure being restrained from distorting, they follow some relationship, some kind of stress strain relationship. So let us discuss in terms of some mathematics, maybe can be better. So what are the strain consist of? It consists of elastic and plastic component, right? Let's say your epsilon A dash double dash. So this part is elastic and this part is plastic. Correct? What is epsilon y? In the similar way, you can tell epsilon y dot plus epsilon y double dot. And then what will be the shear one? So here I am talking about this plane strain condition or 2D. So in the thickness direction, I'm assuming sigma z equal to 0. Okay. So this will be also something like this, elastic plus plastic portion. And then if we apply this Hooke's law to the elastic strain, what is epsilon x? What is this? I hope you have come across these equations sometime. I'm not sure. And epsilon y dot will be sigma y minus mu sigma x. You have come across these equations, right? So these all I am talking about in elastic range. Can you tell me what is G? So these are all about the solid mechanics thing. What is G?
Well,
Sorry,
modulus of rigidity.
I'm not getting you. What is G?
Modulus of rigidity.
Modulus of rigidity. You can tell shear modulus, right? Now, in plastic state, what should be the equilibrium condition? How can we find out the stress? What should be basically your stress strain relationship? So I'm writing down a final equation. right? So, uh-huh. So because of some non-uniform, non-elastic strain as happened during any kind of deformation process, your residual stress can generate. So coming to the question, what are the different reasons for welding residual stresses? What are those? So one is differential thermal expansion and contraction of the weld metal. Is this true or false?
True.
Good. This is true. Then, as I was saying, there can be inhomogeneous plastic deformation. This is also true. And there can be some difference in your elastic modulus property or some heterogeneity in your material. Because of that, also there can be some uh, distortion or deformation associated with this change in elastic modulus, right? So all of these are some reason to induce residual stress in your weldment. Now if we try to understand in terms of what are the typical residual stress arised in your welding. Up to this, any question?
No, sir.
No. Okay, first let me draw a figure. So let's say this is your welding plate. This is my welding plate, and somewhere here this is my melted region. Okay, this is my melt region, and let's say this cross section is b dash. This is point O, and say this cross section is a dash, and this cross section is CC dash. Okay. So this is infinitely long towards this direction. Correct? I hope you understand what it is. This infinitely long. So typical changes in temperature and these thermally induced stresses during welding. So basically, I want to talk about that. Correct? So this is kind of bid on plate well deposited along this line. So this is, let's say, your xy line. Okay, and the welding arc is moving at a constant speed. The welding arc is moving at a constant speed, say v, and for this specific figure, what is it? uh, it's like at the moment at point O, your welding is happening here and you have melted this region, right? So what we are trying to understand is how your residual stress will means how will your residual stress will vary at different locations during your welding zone. So at this region, how will be your residual stress? At this region, how will be your residual stress? Those things we are trying to figure out, right? So the distribution of temperature transverse to this weld line, transverse to this weld line. For this welding, four locations we will talk about. One is away from this melted region towards this side, away from melted region, but towards the welding direction, and some more at some more distance, which is your, let's say, D location is here, DD dash. Okay. So what will happen along the section AA, which lies just ahead of this welding source? Will there be any temperature change really
No.
here at this cross section? You are starting your welding from here. So virtually or ideally to say the temperature change due to this approaching arc is virtually zero. So if you see here for this AA cross section, there will be no change in your temperature, and so there will be no change in your stress also. Got it? And what will happen along section BB? So along section BB, the distribution of temperature will be very steep, right? As this section passes through this arc, some short distance behind the arc, the temperature distribution will be less severe because the cooling will be already begin. So whenever you are going into this direction, initially the temperature distribution will be, it will shoot up, and then when it goes away, it will start to cool down. Correct? Any confusion up to here?
No, sir.
Okay. Same thing will happen for this section also, but the profile will be a little bit flattened, right? And still further back along section DD, that will far away from this weld zone, the temperature distribution along the line has some dropped back and to near some before welding has begun. So it's like here also your temperature, there will be no temperature gradient as such. And how the distribution look like, the distribution of residual stress, the distribution of residual stress in the x direction. So this is your x direction, okay? This is my x direction, this is my y. Let me take another color. So what will happen for the distribution of residual stress in x direction at sections AA dash, BB dash, CC dash, and DD dash? So at section AA, what will happen? There will, as I was saying, there will be no thermally induced stress due to welding are almost zero. The temperature difference, right? So stresses in regions immediately below the arc and the weld pool in section BB dash are almost zero because molten metal cannot support a load. So where there is at the center, the molten metal cannot take any load. Okay. So there the stress in that region will be almost zero. And stresses in heat affected regions on either side of the weld pool, how they will vary? There always exists some kind of stress, and they are compressive in nature because thermal expansion in those very hot regions is restrained by the surrounding metal at lower temperature. correct? So just here there will be this compressive residual stress, and from away from this region here, here we will have tensile residual stress. So basically, this limit of this compressive stress is set by the yield strength of the metal in that heat affected region, where the temperature is highest, which is the fusion zone. The yield strength is lowest. Correct. In the fusion zone, your yield strength will be lowest, and yield strength increases with increasing distance from this weld pool. So compressive residual stress increases to its peak level. So here it is at peak level, right? And at some point away from this weld line, tensile stress will arise to balance this compressive stress induced by this thermal expansion. And what will happen to section CC? CC dash. So here the weld and heat affected zone have cooled considerably, right? And as they did so, they tried to shrink here in the center. They tried to shrink. So if they're trying to shrink, what kind of stress will generate here? At the center, if they are trying to shrink here,
Inside.
great, they will generate tensile residual stress, and away from here, here you will feel, to compensate this tensile residual stress, you will have uh, compressive region over here. Understood?
Yes, sir.
Great. Great. So, I have explained a lot till now how the residual stresses will happen, what are the causes of residual stress. So, regarding this question, the development of residual stresses and distortion in fusion weld structure, w- what is the reason basically? Is this because of non-uniform heating? Is this because of non-uniform cooling? Both heating and cooling? Of course, not this one. So this is very simple question. C is correct. So I hope you are getting the aspects of this how this residual stress generate in your weld structure, and at different location of welding, what kind of residual stress generate basically, will it be tensile, will it be compressive? So those things we have discussed till now. If compressive residual stress is better or tensile residual stress is better?
Compressive is better.
Right. So always keep it in mind that compressive residual stress is better than tensile residual stress. So here for this question, so here for this question, compressive residual stress in weld joint, it decreases tensile strength, it increases cracking tendency, and in increase fatigue strength. So just looking at these three options, which one is beneficial for you?
Third one.
Sorry,
Third one.
third one. Right. So in terms of these effects of residual stresses, or like the consequence of a residual stress introduced in a structure during welding can be detrimental, right? So basically, these effects often result from the way in which they alter these applied stresses through interaction between the two, between this tensile and compressive, how they are behaving. So all this matters, and the major exception is effects on this corrosion, which depend only on the residual stress unless they are altered by an applied stress in some way that either reduces or either reducing the situation basically, you know. So so if you want to summarize what will be the effect of residual stress, let me summarize and write it down. So you're talking about this effect of residual stress. So point number one, what will happen? Effect will be significant only for phenomena that occur low applied stress. What are those? There can be some brittle fracture or maybe fatigue, or I talked about the stress, corrosion, cracking. What next? So whenever your applied stress level increases, your effect of residual stress decreases. Because what is the reason behind this? Because higher applied stress overwhelm the residual stress by causing generally yielding, right? And then what is the next one? So these are few points I want you to keep in your mind. Effects of residual stress on performance of this welded structure under your applied stress is greater than the yield strength is negligible. What else? Effect of residual stress tends to decrease after repeated loading. Okay, so residual stress, as I was saying, they affect the performance of weldments in several ways. Like they reduce the fracture strength of a metal, often to very low levels, of course, and resulting in this rapid and brittle fracture. Right, as I talk written down here, and the cause of this brittle fracture, uh, like what should I mention? The cause of this brittle fracture is largely the complexity of this stress state. So your stress state, of course, it will be always triaxial, right? I hope you know what is triaxial. So you'll have stress at all the three directions. Okay, and because of this complexity in your stress state, there's a because of that thing, the brittle fracture will happen very quickly, and this residual tensile stress causes more problem than residual compressive stress. And this situation even maybe worse when you are approaching to impact, maybe. So like the dynamic loading, you know, whenever you are doing some dynamic loading, or let's say you are doing some what should I say, crash kind of thing, or impacting something, the situation is very much worse, and it will fracture just like this. Because of that, if you are having some internal stress or residual stresses in between. Okay, moving to next question. Just wait for some time. It needs some more time. Huh. So which of the following is incorrect for this tensile residual stress? So it says it reduces the fatigue strength. Is it true? Tensile residual stress, can it reduce?
Yes.
This is false. This is also false. Tensile residual stress is very much detrimental. It cannot reduce anything. So, aha, this is true, right? It initiate the failure due to fracture, and then because of your fracture propagation and tensile residual stress is presence of this tensile residual stress, you'll have some brittle crack, right? That was the thing I was discussing till now as an effect of this residual stress. Okay. So coming to this different measurement techniques of this residual stress involvements, what are different techniques available? So there must be some effective way to measure such stresses, right? So like neither analytical nor some numerical model based simulation cannot be believed without any experimental verification. So measuring this residual stress, including its magnitude and the size. So is it tensile or is it compressive? As a function of location, possibly in three direction is far from trivial in reality actually, if it is not in principle, of course. So there are many methods for measuring this residual stress in metals. Uh, like there can be something called stress relaxation method, then there can be some X-ray method, and more recently there has been this neutron diffraction method. As you have, I don't know uh, you're aware of this or not. And then there can be some cracking methods also. While no method is perfect by any means, each has its merits and limitations, right? So, so yeah. So as I was saying, there can be different techniques. One is this stress relaxation technique. So what happened in stress relaxation technique? So for this method for measuring residual stress are all based on the fact that straining that takes place during unloading, or basically when you're removing or freeing a material is elastic, right? This is an assumption even when the material may have some undergone plastic deformation. So this is assumption for this technique, stress relaxation technique. And this being the case, it is possible to measure residual stress even without knowing the history of the material, right? So, so a variety of this specific technique is available. Like there can be something called uh, some sectioning technique using electric resistance strain gauge. What happens there? So in this technique, gauges that measure strain or the displacement by the change in electrical resistance in a coil of wire or foil that are mounted on the surface of this let's say your test workpiece, right? A very small piece of material contains this strain gauge in the weld or adjacent to the weld, which should be carefully removed by machining just to introduce this additional strength, right? And by keeping this extracted piece small enough, no residual stress can be sustained. So the strain measured by the gauges placed on the removed piece that can be used to calculate this elastic strain. And also this here, whatever gauge you use, they're generally mounted 120-degree apart to facilitate this calculation uh, using the relation. So the relation is like, okay, let us not. We just talked about that mathematical relation of the stress strain. Anyhow, uh, so this is one of the sectioning technique using this electrical resistance strain gauge. This comes under the stress relaxation technique, and then there can be something called Rosenthal, Norton section technique. So this technique is now out of order. Like people don't use this kind of technique now. Uh, so just to say anything for this technique, this is intended for some application to thick section weldments and to work this to narrow. Okay, we can skip this technique, and then there is something called uh, method sweat hole drilling technique. So this is basically a hole drilling technique for measuring this residual stress. And when a hole is drilled in the mid of some rosette pattern of this resistance strain gauge, the gauge register a change in strain, right? And this is the result of this res- localized removal of restrained by material removed from the hole, and some kind of localized distortion will happen in response, right? And then some residual stress can be calculated if the distance between this hole and the gauge length is known. So that is the method for this hole drilling technique. Don't go into the depth as of now. Just I'm mentioning the different kinds of techniques what is available for this measurement of residual stress. And then there is something called uh, Kuhner drilling technique, right? And finally, you have this X-ray diffraction technique. So finally, you have so I am familiar with what happens in X-ray diffraction, not with these techniques as such. Honestly, to say so, like X-ray diffraction, it has been used to measure residual stress for years, basically. And obviously, the technique requires some expertise, especially if high accuracy. If you want to have some high accuracy, and this technique relies on residual stress causing the normal lattice spacing of a crystal to change, right? So how this XRD works basically? Let me draw a figure. So in XRD, if you see, you'll have some camera over here, and then you can have some film kind of thing, and here your X-ray is incidenting. So we call it an incident beam, and then you have your samples, right? You have your samples, and there can be some mirror here like this. And let's say my sample is having this atomic planes over here at some direction. So it must have some crystallographic direction and crystallographic plane, right? and depending on that crystallographic plane and direction, it will basically diffract a beam. So this is my diffracted beam, and this angle is 2 theta. You're well aware of this Bragg's law. I'm not going into the Bragg's law. Same way it works. So coming to the question, which of the statement is correct about the brittle coat method for measurement of residual stress? So you need some aluminum pre-coating to provide a bright background. Yes, this is true. Only calibration strips are sprayed. This is false. And you need to have some hole of some specific dia, which is 3 mm, to release the residual stress, right? Basically what happens, like whatever methods I discussed, like these stress relaxation techniques or the sectioning technique using electrical resistance, then your Rosenthal Norton or this cold drilling techniques, in all these methods they use some kind of coating that change the color with different strains, some kind of coating, or you can say some brittle coating that exhibits strain release in the form in the form that is maybe location or direction or pattern or some kind of severity. So some kind of uh, what should I say, some kind of effect should be there to understand what is happening there, right? Huh. So this is regarding this this question is regarding this controller, if you want to remove this residual stress, you know. So in terms of this controlling or removal of residual stress, although this effect of residual stress on the service performance of the welded structure, it can vary significantly, right, depending on their severity and impact of their occurrences. There can be variation always. So it is generally preferable to keep the residual stresses to a minimum for the obvious reasons what we have discussed till now, right? So precautions to reduce this residual stress, it can take two forms. Like there can be prevention or there can be remediation, right? So to prevent this development of residual stress, it is crucial to reduce the effect of heat during welding. Whatever you are producing in terms of heat during welding, that you need to control always to prevent this development of this residual stress, right? So one way what it can be, you can employ some cold or some non-fusion welding process, but this is seldom a viable option, of course. And yes, of course, there is some friction stir welding. Are you aware of this solid state welding, where you don't need to do any kind of fusion as such? There will be some deformation or mechanical intermixing and forceful intermixing of materials, and solid state diffusion happens basically. Whereas in terms of fusion welding, It's always liquid state diffusion, which is very much rapid. So, are you aware of the solid state welding? Hmm.
Yes, sir. Some processes.
Okay, that's okay. So, huh. And then, as I was saying, one way can be you can employ some cold or non fusion welding process, or else another approach can be you can employ some hot non fusion process. There is always there is another technique called what it was huh, some cold spray, not cold spray, uh, cold metal transfer welding. You can Google it. So here you can control the heat affected zone or welding zone in a narrow region. So whenever you are reducing or narrowing down your heat affected zone, uh, the region is basically where you are getting this what should I say, this columnar kind of dendritic structure that will be much smaller region, right, compared to some conventional fusion technique. So you can go through this cold metal transfer. You just take a look what is it. And so what I was saying, that another approach can be hot non-fusion process to eliminate this shrinkage associated with this solidification of any kind of fusion zone, right? So in hot non-fusion, there can be still some thermal contraction in any kind of heat affected zone that must be dealt with some tolerance or some allowance, right? But the major source of this residual stress will be the volume shrinkage, right? Volume shrinkage upon solidification that must be eliminated. Uh, what can be the third approach? You can minimize the volume of the molten weld metal, as I was saying in for cold metal transfer welding, and also mechanically how you can do this can be done some proper choice of some joint preparation. For example, let's say your uh, let's say U groove could be used in place of a V groove, because U grooves will require less filler material, and also it is also desirable to use the smallest group size and the smallest angle. And there are some geometrical features, of course, for this V groove. uh, you need to play on these geometrical features to have some less heat affected zone, right? What else? So in terms of prevention, we can work with these things in terms of remediation of residual stress once they arise in a weld mill is accomplished by this post weld thermal treatment, right? So as we are talking about this heat treatment or thermal stress relief, so heating basically lowers the yield strength of the base metal, and it allows localized relaxation of residual stress, primarily by some kind of plastic deformation, or maybe some creep is happening. So this effect of time and temperature, those plays a big role in this residual stress thing. No? So coming to the question, so which of the statement is correct for pinning process? I hope you are aware of this. There is different kinds of pinning that can be laser pinning and some kind of hammering also. So it's basically you elongate the outer fiber of the weld with the help of some mechanically hammer. So if you are having some tensile residual stress in between your weld metal zone, so if it is trying to make some crack, whenever you are hammering it through all over, the crack will not elongate and propagate. It will try to shrink there. So basically, brittle fracture happens because of initiation of crack, and then it just propagates all over, right? So whenever you are, let us say you have some initiation in crack here, but due to some application of this hammer blow, it cannot propagate like happen in brittle fracture. Maybe there can be some another place where there is initiation of this. It just diminish away from here. So pinning process always helpful to suppress this crack propagation thing, and also it is used for this stress relieving purpose. So both one and two are true for it here in this question. Any question?
No, sir.
So the last two are simple, like simple objective question. It says which of the following is not among the method for measurement of residual stress. So as we are saying that you have the strain gauge method, you use it for measurement of residual stress. You can have this brittle port method. I have just mentioned one method which is laser scanning. Actually, we do some X-ray diffraction. There is nothing as such laser scanning method for measuring residual stress. So this is the right option. And then in the final, which of the following is the method to reduce the residual stress? It can be, of course, it can be pinning. It can be vibration operation. We can use some thermal treatment and thermomechanical treatment also. So all of these are true. So what is the summary then? Whatever we have learned from this today's session, or from your video lectures. So in summary, we can say that the severity of heating and cooling associated with the thermal cycles, which is of course typical for this fusion welding process, it always results in thermally induced strain and stress, right? And because of this thermal strain and thermal stress, it can lead to severe distortion. So these things are integrated: residual stress and distortion, right? Any question from your side?
No, sir.
Yep. Okay. So we'll finish the session here. We'll meet next week then.
Thank you, sir.
Okay. Sure. Bye bye.